Hi everyone, my name is Moshe Levy. I'm a senior at Rutgers University, majoring in physics and minoring in math. Today I'll be presenting the research I've done for the STAR collaboration. My research has focused on studying the properties of quark-gluon plasma, or QGP, that is produced in heavy ion collisions. We do this by analyzing how the quark-gluon plasma interacts with jets. Jets are collimated sprays of hadrons that result from the fragmentation of partons involved in a hard scattering. As these jets traverse the medium, they interact strongly with it, and their energy distribution is modified. So by analyzing this modification, we can determine something about the medium. So how do we quantify this modification? Well, we look at so-called jet-shaped observables. These observables each measure a different aspect of the energy distribution of a jet. To get a better picture of what I mean, let's look at the specifics of the three jet-shaped observables that we used in this study. The first jet shape we'll look at is Le sub. Le sub is the difference in PT of the leading, i.e. the highest PT jet constituent, and the subleading jet constituent. This observable is therefore large when a single constituent's PT is much larger than all the rest. Next is girth, or G, which is defined in equation 2. From the definition, we see that it is essentially the momentum-weighted average distance of the constituents from the jet axis. So it is large when the jet's momentum is spread out, and small when the momentum is concentrated close to the jet axis. Finally, we have momentum dispersion, or PTD, which is defined in equation 3. As you can see from the definition, it's always less than 1, but it is close to 1 when the momentum of the jet is concentrated in a small number of constituents, and close to 0 when the momentum is distributed among a large number of constituents. So we see that these three observables give a complementary picture of the energy distribution in the jet, and therefore enables us to see how the medium modifies that energy distribution. For our analysis, we looked at data from 200 GeV, AU, and PP collisions measured at the STAR detector. The PP serves as a baseline since no QGP is expected to be produced in PP collisions. We used the FastJet software package to reconstruct jets from the raw data. Specifically, we used the anti-KT jet reconstruction algorithm with the R parameter set to 0.3. R is essentially the maximum radius of the jet cone, though this isn't necessarily always the case. We limited our jets to those with PT greater than 25 GeV per C and absolute value of eta less than 0.7. Additionally, we imposed the constraint that all jet constituents have PT greater than 2 GeV per C and absolute value of eta less than 1. These cuts are mostly for the purpose of mitigating systematic uncertainties. Then with the jets that make it past the cuts, we calculate the jet shapes. We split our jet shape distribution into centrality ranges. Centrality is a measure of how head-on a collision is. The reason for doing this is that the largest amount of QGP is produced in the most central collisions and the least amount in the least central. So by looking at different centrality ranges, we get a more detailed view of how the AU distributions differ from the PP. Our results are presented in these three figures. At the top of each figure is the distribution of the jet shape for the four centrality ranges of AU collisions, as well as for the PP collisions. And at the bottom, we see the ratio for each of the AU centrality ranges over the PP. If we look at the ratio plots, both Le sub and PTD differ from the PP distribution in the most central distributions. This hints at medium modification of the jets. However, these results are not yet corrected for detector efficiency and acceptance, so these observations might change. If we look at the girth ratio plot, it doesn't seem to have the same trend as Le sub and PTD, so perhaps the radial distribution of momentum as measured by girth isn't affected by the QGP. But again, these results are not yet corrected for detector efficiency and acceptance, so these results might change and we can't make any physics conclusions. The next step with this study is to apply the appropriate corrections so that we can make legitimate conclusions from these results. We will also examine the dependence of these measurements on jet PT, in addition to the centrality dependence that we have already shown, to get a more complete picture of how the medium modifies the jet.